So my name is Nikos Pantelelis. I'm director at Synthesites in Greece. And as I said, we are partners in the Morpho project together with the other presenters. And my co-chair today is Simon Waite, senior expert for materials and at certification directorate at EASA. EASA is also a partner in Morpho project, and Simon will give us, let's say, an overview of what EASA thinks in respect to the Morpho project and the challenges we had. So the speakers today will be Vladislav Reimer. He will speak about the development and application of fiber optical sensors for resin transfer molding and structural health monitoring. Then will be followed by Andreas Krenz from IFAM, but he will speak about the integration of fiber Bragg grading sensors in CFRP RTM parts and data analysis for resin flow monitoring. Then he will be followed by his colleague Igor Wirth from IFAM again, IFAM. He will speak about printing of sensors on composite components for aerospace applications. Then I will present our part, the work that we've done in Synthesites about the intelligent and reliable monitoring for composite molding. And finally, we end with Eric Monteiro from ENSAM. He will speak about the hybrid twin for online monitoring of resin transfer molding process. Let's start with Simon.
Okay, thank you. Again, I've been involved with this project for a while, representing EASA. My background, for those who don't know me, is I was putting fibers in composites back in 1988, but that was long before the luxury of fiber Bragg grating. I was using polarimetric York fiber, which it kind of worked at a very crude level. But so from our perspective, as I've indicated, this project touches quite a few areas which are have linkage to regulation, and quite honestly, we recognise this is an R&D project, but we're more interested in projects that are on the right side of valley of death, in the sense that there are elements that are achievable in the final product. And so we know it's not certification, but any elements along the way in any R&D project which can nudge the technology in a useful direction is worthwhile. In terms of this project, fan blades are already certified as composites in a composite construction, and we know the materials and advanced health monitoring as SHM technologies are evolving rapidly, and we know there are many existing related and established cross-product activities for which SHM is just part of that package. Engines, rotorcraft, and large passenger aircraft are increasingly heading in that direction. And particularly engines and rotorcraft have architectures of system application which are very transferable to the SHM. In a sense, the SHM is about understanding the sensors and the impact on structure, and that's part of the content covered in the presentations today. So also, we've been sharing with Morpho our discussions and opinions along the way, and we've also shared with other parts of the industry, like Commercial Aircraft Composite Repair Committee and the other stakeholders, because this is an end-to-end story. And in the future, maybe we have open rotors where this could have a relevance, but open rotors are a massive challenge in their own right. So So as I mentioned, we basically as regulators have some fairly high level regulations addressing material and process and advanced manufacturing methods. And you'll see those requirements through design, manufacture, and in service. So if we look at design and we think about brag gratings, or we've got to think about how does this impact our understanding of the structure in terms of modeling and simulation, both in terms of perhaps the process for cure, in fact, in terms of what we can interpret in terms of damage tolerance and sensor capability in service. So, how do we do with modeling and simulation? How does this change our test analysis pyramid? We've got to remember we've got composites, which are highly anisotropic and have competing failure modes, and they suggest a need for more testing, not less, which is a bit of a challenge for industry that wishes to use analytical methods to replace testing. So this is one of the big divergences that we're having to address. And fiber brag ratings and composites and this project fit nicely into that discussion. So we have requirements 603, 605, 613, very basic requirements in large airframe, which are very transferable to other products. We have the damage tolerance 571. We have the engine requirements E70, E810. Then we have the means of compliance that support them, for example, AMC 2029 composite structures. Up on the right hand side, you'll see a very simple classic staircase of regulations and what you're trying to achieve in terms of load levels in your structure or your part versus reference points in terms of the regulations. This is shown for structure. You can adapt this and use it in engines. That's what we did for previous products. And you'll see that Rolls-Royce, for example, has been presenting adaptations of damage tolerance interpretation. But obviously because the fibers are both possibly impacting the behavior of the structure, but also, or your sensors, whatever your sensors are possibly impacting the behavior of your structure. But also we have to understand how they change the characteristics in terms of performance, in terms of engineering properties in service. Are they reacting differently to impacts? How reliable are they, etc. And we've been managing this through regulatory tools which adapt this patchwork of requirements through a certification review item. So that's kind of the framework we're working in. And of course, this brings in manufacturing. How do we correlate the embedded fiber sensor or tool sensor data with, how do we correlate that with engineering properties? In service, as I said, impact of sensors upon engineering properties. How do they change this fracture toughness, stiffness, etc. Reaching just to one example, again, airframe, but conceptually, this is the same for other products. We have a basic regulation 571. It says you've got to demonstrate that you're going to avoid catastrophic failure due to fatigue, manufacturing defects, environmental deterioration, accidental damage, and throughout the operation of the aircraft. And then we have the inspection requirement, which is, says the information you have to provide to the user of the product has to be adequate to maintain that safety level and avoid those threats. And it importantly says, and it has said it for a long time, it doesn't have to be inspections, it can be other procedures, and that's the gateway for these other inspection methods into the long established that's existed, and that's the gateway into possible future applications in other products outside those that are already using some of these technologies. And this applies to baseline structure, mods and repairs, and that's quite a big challenge, mods and repairs, in terms of adapting and repairing these systems. So if we perhaps pick on the detail of how we might interpret this requirement, we've got to deal with manufacturing defects. Now, we can get into the semantics of what a defect is, but it's usually something that is an anomaly or flaw that's within the scope of a spec. That's part of the material you qualify it and you substantiate through your test analysis pyramid. Is the inclusion of your sensor going to challenge that? How do we include that within the spec? So that's one of the important aspects that the building block presentations that follow will be starting to provide more confidence for us. So that's just an eye chart, just an example of the vast array of existing requirements which have elements of an SHM system. And I repeat, that system, you cannot separate the elements, the cross-discipline understanding of system versus structure versus material science. It's all needs to be integrated fully. Pulling out the key items for engines, we've got the E515 condition monitoring. That's not new. We have rotorcraft with vibration health monitoring, 1495. Large passenger aircraft, we have perhaps for the future 25302, system structure interaction. FAA has recently produced an AC from an operational perspective and has an issue paper for certification issues. And we have the SAE, SHM, AIRs and ARPs in development. There are various SHM applications just about to arrive, and which I'll talk about on the next slide or two. And EASA has a number of projects that are involved with equivalent life counting, which is the simplistic end of perhaps the health monitoring world. And there are many other R&D projects out there building on the equivalent life strategy. So if we look at what's going on, the reality of SHM, not just general health monitoring, you may or may not be aware, we have a very focused example. We have the 737 rear pressure bulkhead CVM being applied to a very known crack case on metallic structure. This is the right way to go to build up the approach. So that's insert plan submission with the FAA. We're expecting it. We've already got a task allocated to it. So that's on the rear pressure bulkhead. We also have a dedicated possibility of antenna interface, have an STC, or a supplemental type cert application of antenna being built and then placed on a baseline structure. And there's an interface problem. So this approach here from Delta is using sensors to perhaps find damage at that interface, which is problematic for operators. So it's very real. So summarizing, we expect to see small steps in terms of criticality and complexity. For example, the rear pressure bulkhead external sensor example is a very good one because it's very focused on specific known crack and it's very limited, and that's the way to go. But we're a long way from on condition monitoring of extensive structure areas. The small steps we take have got to be parallel with and don't compromise existing airworthiness process. And we've got to deal with understanding appropriate and using appropriate experience across technical disciplines and product ranges. Let's use what we've understood and learned from other technologies and other products and use them selectively when they help us rather than create a divergent world. So we know the safety challenges are probability of detection and system reliability. And again, that's going to be part of the building block discussion of where fiber brag ratings are going, perhaps as a means of dealing with the application for fan blades. We need to use the regulatory process, and we're patching together the existing regulations through the certification review items to try and work out how the future regulations might look. So it is typical building block process for us. And performance-based regulation, i.e. the movement to performance safety outcomes rather than prescriptive regulation, is also in progress. And this is quite a challenge for us because there's a need with new technology to both have a prescriptive understanding of what's acceptable. At the same time, there needs to be flexibility to have many approaches to the final outcome. This is a big challenge for us. So basically summarizing, discuss intentions early with the regulators is my basic message. And you'll see on various presentations, this is the contact points I have in EASA relating to various disciplines and products. So if you wish to talk to somebody at EASA on the particular issues, rotorcraft systems issue or whatever, go in here and use these as the first contact points. This spreads the knowledge through EASA and helps us to coordinate in a sensible way. So I hope that was a fairly quick outline of where we're at